Welcome everyone to the IS Missing Data Challenges workshop. We are very excited to have everyone here. As many of you know, we were originally going to have this workshop in person in March, and it was canceled. I don't know if it was even 7 days before the workshop, because the time was, really at that early moment when people were figuring out that travel and so on was a major factor in spreading COVID. So we postponed until now, and we're actually very excited to have it online on Zoom now that we're all more used to it, first of all, but also because many more people are able to join us. So that's absolutely wonderful. I probably don't have to pitch this to the audience who chose to join this workshop, but missing data is a challenge in basically any problem where data are collected. Machine learning problems, statistics problems, in healthcare and government, in industry, and even more areas, because it's almost always impossible to collect all the data that you want, and even when you try, there will pretty much always be issues with data collection. And missing data is one of the most prevalent. So we're very fortunate to have this week 4 half days. Today will be in the morning, and then Wednesday through Friday, partial afternoon, Friday ending on the earlier side. But in each one of those, we have wonderful speakers who have worked on the problem of missing data from a wide variety of perspectives. The good thing about that is that I hope some young researchers who are watching and paying attention will see that there are many, many exciting problems to solve, and that they need some interdisciplinary understanding of the applications, the statistics, and the algorithms in order to get them solved over the next coming decades. So, hearing from all these different perspectives will hopefully help us see how wide our field really is, when sometimes maybe we work on a specific problem and only see it from that narrow perspective. Okay, so logistical issues. Each day there will be a chair for the day, either I or Bianca, one of my co-organizers. And just to mention, so I organized this with Bianca Dumitrascu and Boaz Nadler. We were together at the Institute in the spring, and we had, or sorry, I should say in the fall. Boaz was there in the fall. We had many wonderful conversations, and we were very excited about this topic. So we decided to host a workshop on the topic. So one of us will be chair of the day, and sometimes we'll chair a session. We also have some others who have agreed to help us chair a session. And the chairs will be responsible for looking into the chat. And so if you have any questions as an attendee, you can't speak or have your video on, I believe. So if you have any questions, then please type them in the chat to everyone. And the chair will be monitoring that chat and will interrupt the speaker at an appropriate moment in order to ask those questions, okay? And certainly if it's a question for clarity or whatever, then try to share it right away, because we want everyone to be on the same page with what the speakers are sharing, okay? Also, if you have any questions or logistical questions, feel free, you could put them in the chat directly to me or Bianca, Boaz, or also Michelle Hugenin if she's on periodically throughout the day to check in on us. Okay, so that's all the comments I have to get started. We still have 1 minute, so that gives me time to introduce our speaker, Rod. I'm going to stop sharing so that you can take over, and I will introduce Rod as we get started. So Rod Little is the Richard D. Remington Distinguished University Professor of Biostatistics at the University of Michigan. I'm very fortunate to have someone of his stature and experience to share ideas with at my university. Early in his career, Rod was a research fellow at the U.S. Census Bureau, which is I'm sure all of you have thought about recently. It has many, many interesting problems in missing data. And he then served as a member of the Committee of National Statistics. He chaired an NRC study on the prevention and treatment of missing data in clinical trials. And from 2010 to 2013, he served as the chief scientist at the US Census Bureau. He's an ISI highly cited researcher, has received the Wilkes Memorial Award from the American Statistical Association, and is a fellow of the American Statistical Association, the Academy of Arts and Sciences, and a member of the National Academy of Medicine. So we're very, very fortunate to have Rod here to start off our Missing Data Conference. So go ahead, Rod, and I will be monitoring the chat for any questions.
Thank you very much, Laura, and thank you to all three of you for doing this. It's a challenge to have a meeting by Zoom, so but you seem to be. Congratulations on pulling it off, and I look forward to the meeting. Can people see my screen?
Yes,
okay, good. I'm getting nods, so
I can see them.
It's a pleasure to be here. I was telling the guys that my background, I like to sing. So this is the Michigan Renaissance Festival from last year. I sing in a madrigal choir. So one of the horrible things about the COVID is not being able to sing, since it's one of the great pleasures. So anyway, here's what I'm going to talk about. So I thought, since this is the first talk, and since I'm an old guy, I should give a kind of a historical sort of overview of the missing data literature from my own statistics perspective, not so much the machine learning. So I'm proposing to, I'll give a very brief historical overview of how people have approached missing data, and then some of the key ideas in the literature, modeling the missingness mechanism, missing at random assumption, maximum likelihood and Bayesian methods, multiple imputation, missing not at random models. So I'll talk about those, which I view as kind of key ideas in the work that I do. Then I'll talk a little bit about differing perspectives for probability modeling versus the more algorithmic machine learning type approaches, which I'm sure some of you are doing. And a little bit mention the fact that I think it's important to be clear about what the goals of what you're doing are, since in particular, are we interested in making inferences about parameters in a population or superpopulation, or are we really interested in predicting the missing values? Sometimes I think these goals get a little bit confused, and since they have different implications for methods, I think that's important. So first, I'll put a shameless plug in for my book on missing data with Don Rubin. Since we just finished, got the third edition of the book just came out in 2019. So I put a picture of the book because I actually designed the cover. This was one of the things I kind of liked, I feel rather proud of. So I'll occasionally refer to pieces of this book, since it sort of figures into what I'm going to talk about here a bit. Don is on the left there. I don't know if you checked how many citations Don Rubin has recently, but it's about 440,000 if you're interested. Puts us all to shame. So this third edition, just for those of you who know the book, some of you may have looked at it, we do have a bit of a revised treatment of missing not at random models in the last chapter of the book. I think one of the things that did change in the third edition was they were a bit more systematic about that, and I have a slide about that in this talk. We got some flack on why NIS standing for missing values, why OBS standing for observed values. essentially because this notation creates some confusion amongst some people as to whether you're actually conditioning on the missing data pattern when you say why miss and so on. So we actually went back to the original notation in Rubin's 76 paper and changed that notation. We also have a bit more precise treatment of conditions for missingness, ignoring the missing data mechanism or missingness mechanism for frequentist and Bayes inference. And I just recently did a review paper on this that did a little bit of additional work on it. And then we have some new examples in the book. One of the interesting, nice things about missing data is that you can treat a lot of other problems in statistics as missing data problems, like measurement error, sensitive, and then also causal inference can be thought of as a missing data problem. And then examples on sensitivity analysis in clinical trials. So a bunch of other examples in it. We didn't add a lot of extremely new material since the field has become so broad now that it would be impossible to cover everything that happens in missing data, besides which I'm not very good at reading the literature anymore. But it's better to, I think, to focus on the stuff that we knew. So we didn't make radical changes to the structure of the book. So what do I mean by missing data? So I think it's important to have some idea. So we're thinking mainly about a situation where you have a rectangular data set. Here I have the rows of the units or the cases, and then we have variables, and then we have gaps in the data. So those are the white parts of the little diagram here. And so the question is, if you were to fill that in, if you were to impute it or something, would it be meaningful for analysis? So it's missing data if the underlying value that's missing is meaningful for analysis. That's the way I define missing values. So if you miss a clinical visit in some clinical trial, for example, it's reasonable to suppose that the values that you didn't observe in that missed visit are meaningful for analysis. So that would probably be missing data. On the other hand, let me skip the middle one, but for the last one, in a longitudinal study of blood pressure medications, treatments for blood pressure, high blood pressure, if you have a loss to follow up, then that might be considered missing data. People have a blood pressure that they didn't show up for the recording. Deaths, however, if people were not in the study because they died, they didn't have a blood pressure, at least not a meaningful blood pressure if they're dead. So that I don't regard as being a missing data problem. And there are lots of other sort of situations that are somewhat intermediate. So sometimes it's a little bit complicated to actually decide whether you really have missing data or not. Laura kindly mentioned this National Academy study that I chaired, and one of the main findings of the National Academy study on missing data in clinical trials is just don't have missing data. So, and the reason is that every missing data method, whether you take a model-based perspective, which is my perspective, or if you take a machine learning algorithmic type perspective, everything involves assumptions. There is no way of dealing with missing data without making assumptions. If those assumptions are violated, then the methods will not work very well. In model-based approaches, the assumptions tend to be, in a sense, explicit in how you're formulating the model. You write down a model, you make assumptions about distributions and what variables are predictors of other variables and so on. The assumptions are explicit in the model formulation. In algorithmic approaches, the assumptions tend to be unstated and implicit, but the fact that they're unstated doesn't mean that they're not there. So you can't avoid assumptions by just not stating them. And my view is that they're always lurking in the background. So for these reasons, whether you're a machine learner or whether you're a statistician like me, you're better off not having missing data. And this National Academy study talked a lot about how to avoid having missing data in studies. by having, for example, a committee that keeps a handle on what the missing data rates are, chases after sites that are bad at it, or limiting respondent burden in questionnaires using matrix sampling, things where you don't ask everybody all the questions, collecting information that helps to predict missing values, following up a subsample of non-respondents. Laura mentioned the census. Well, so census has this very large non-response follow-up. So don't have missing data, but we do. So if we do have missing data, here are some three sort of general strategies. So there's imputation, where you fill in the missing values by plausible values. Multiple imputation, I'll talk about later, being a version where you do that more than once and create multiple data sets. Complete case analysis, where you basically discard the incomplete cases and only use the units that are fully observed. You might weight them. So in the survey setting, survey sampling, we use non-response weighting as a common method to try and correct for the fact that the complete cases may not be a random sample of the original sample. Or you can use a method that doesn't require a rectangular data set. So maximum likelihood or Bayes, things that are based on a likelihood, you can create likelihoods based on the incomplete data without ever filling anything in. So that's another general strategy. So here's my own potted history of missing data methods in statistics, which actually goes back quite a long way, at least into the 50s and 60s of the previous century. And before the 1970s, people tended to handle missing data by relatively ad hoc kinds of methods, just either discarding the data that had any missing values or plugging in the mean for values that are missing, or the last observation carried forward in a longitudinal study. Relatively simple ad hoc methods. Then, in a way, I think the first sort of systematic approach to the subject was to use maximum likelihood, which T.W. Anderson, who's a famous statistician, he died actually last year, I think, from Stanford, did maximum likelihood for relatively simple problems. And Anderson had a very nice paper, which I'll mention, called using the factored likelihood. So the first systematic approaches tended to be maximum likelihood, but maximum likelihood for complex problems involving iteration was perhaps too hard in those early days because of the lack of computing. Then I sort of call the 70s to the mid-1980s the maximum likelihood era. So Rubin in 1976 had this famous paper on modeling, on defining missing at random. And the key idea was basically to model the missing mechanism. Now I'll say a bit more on that in a minute. Then we had better computing. In particular, we could do more iterative kinds of computing algorithms. So there was the EM algorithm, which probably a lot of you have heard of or know, that was systematized in a paper by Dempster and Rubin in mid-70s. Actually, Orchard and Woodbury actually had an earlier version of this in the early 1970s, but it was kind of an obscure paper, and so it didn't get as much play. And then extensions of EM, this algorithm facilitated maximum likelihood for more complex problems. There was a lot of maximum likelihood for various models that go beyond just the multivariate normal data, multivariate normal model for missing data in a rectangular data set. And the first edition of my book with Don in 1987 talked a fair bit about maximum likelihood for these different models. From the mid-80s to the present, the change which I find is important from my perspective was a move perhaps away from maximum likelihood towards more Bayesian methods and the related method of multiple imputation. So it's a paper by Tanner and Wong in JASA in the 1980s, coined the term data augmentation, which was basically solved the missing data problem and created a posterior distribution for multivariate normal data with missing values. Data augmentation turned out to be one of the first implementations of the Gibbs sampler, and it really differed slightly from the Gibbs sampler, but not very much. So this is a very important paper. Rubin also proposed multiple imputation, which I'll talk about in a minute, which was justified by Bayesian methods, but also is also, I think, good idea from a frequentist point of view as well. So the original paper on multiple imputation, 1978, I remember reading this and thinking, this is crazy. Nobody could do this. It's such a wacky idea. But of course, everybody does it now. So that's what makes you a great researcher, right? You make up stuff that then everybody thinks is crazy, and then everybody ends up doing it about 20 years later. So so we can do Bayes essentially because of Markov chain Monte Carlo type methods simulating posterior distribution. So Markov chain Monte Carlo methods like the Gibbs sampler facilitates Bayes and multiple imputation as an alternative maximum likelihood. And I would argue that Bayes is better than maximum likelihood, and I'll say why in a sec. Then since the 1990s, there's been quite a lot of work in statistics of trying to weaken distributional assumptions, in particular, so in improving the robustness of methods. So Jamie Robbins and colleagues proposed this augmented inverse probability weighting, sort of an extension of inverse of probability of the weighting method, for handling missing data. And there's a lot of more references. I just put Robbins and Rotnitsky in there, a JASA paper. From a modeling perspective, more robust models, and also more attention to checking models, so model diagnostics sort of came into play more. And in recent times, I think people have been interested in dealing with missing data with more complex models. I think of latent class type models for categorical data, and Bayesian additive regression trees, which is a tree type method, which I kind of like personally. So there's more sophisticated models. I mean, you can apply neural nets, things like that, and I'll say a bit more about that later. So that's my sort of history. I don't know if anybody has any questions at this point, but I can stop for a bit, and if anybody wants to make a comment, then feel free.
Please go ahead and put questions in the chat. We don't have any yet, though.
Okay, so I'm going to briefly review some of the seminal developments as listed here. So, so the modeling the missingness mechanism. So, 1976 Biometrica, Rubin proposed this, wrote this paper that Don likes to say was rejected by all these other journals. So it was rejected by a lot of the American journals, and it ended up at the desk of Biometrica, where David Cox was the editor. I happened to be, this is at Imperial College. I happened to be a graduate student at Imperial College, so David Cox gave me this paper to referee. So I wrote this very long referee's report saying that I thought there were some problems with the paper, but Cox wisely ignored them and published the paper anyway. He allowed me to do a discussion, which I think has 0 references. But it's a good discussion nevertheless. Anyway, Don's paper now has getting on for 10,000 citations, which is relatively minor number of citations compared to some of his papers. EM has, I don't know how many citations. Anyway, so that was the story. That was my first paper I refereed, so fun. The key idea of this paper was to model the missingness mechanism by treating missingness indicators, an indicator for whether a particular value was observed or missing, as random. So essentially including them as part of the statistical model and assigning them as statistics, a distribution. then he provided sufficient conditions under which the missingness mechanism can be ignored for likelihood and frequentist inference about parameters. I'm going to focus more on the likelihood and Bayesian conditions here. So a little bit of notation, and I'm not sure if I was totally consistent with my notation throughout the presentation here. I apologize in advance. So anyway, D is this rectangular matrix with no missing values. D1 is the observed part of D, and D0 is the missing part of D. And then there's a response indicator matrix or a missingness indicator matrix. A response indicator 1 if the value is observed and 0 if missing. Missingness indicator is 1 if it's missing and 0 if observed. So R is just the I minus M, if you like. Then so Rubin modeled R as a matrix, as a random variable. So he had a joint distribution for D and R, and he factored it into the marginal of D, which is the complete data distribution, and then the distribution of R given D with some other parameters. So then you can form a full likelihood by basically integrating out D0, which are the missing values, from the joint distribution, and that creates a likelihood based on the D1 and R. Or you can do a likelihood ignoring the missingness mechanism, which doesn't include a model for R, where you just integrate out the missing values from D, but you'll see on the right-hand side of that expression that there's no R, so essentially R is being ignored and not being included as part of the model. If the full likelihood factorizes into the ignorable likelihood plus something else that doesn't depend on theta, theta here are the parameters of interest, and if theta and phi, the parameters in these two distributions are distinct, then you can basically base the inference on the ignorable likelihood, and that's called ignoring the missingness mechanism. And I think I've skipped a. It looks like I lost a slide. So I apologize, I've missed a slide, which I'll add to the deck later. So Rubin gave conditions for ignoring the missingness mechanism. And essentially the conditions, there was this distinctness condition that theta and phi were not related. But the main thing is that for likelihood inference, missingness, the distribution of R, can only depend on the observed part of D, but that doesn't depend on the missing part of D. And that's the missing at random assumption. So Rubin basically showed in this paper that under missing at random and distinctness, you can ignore the mechanism. He also talked about frequentist inference. Well, that's more complicated because it depends what you mean by frequentist inference, which is less clear. So actually in a paper a few years back with Don Rubin and a student of mine, Zhang, we also gave some conditions for missing at random for a subset of theta, rather, because sometimes there are particular parameters within theta that you're interested in, and this is a similar condition under which we call partial missing at random that that applies if you're really interested in theta 1, but theta 2 is kind of a nuisance parameter, and that has some value because in some
Oh, I'm sorry.
Okay, let me just finish my sentence. And so that has some values because there are some situations where you have partially missing at random, but you don't have missing at random. So it weakens the condition somewhat. Yeah, go ahead, Laura.
There's a request for clarification of what phi and theta are representing. So the question then Boaz added, it seems a parametric setting in the goal is to estimate these two? Or?
Yeah, so this is a parametric setting, and the goal is really theta. So I mean, the simplest case, a very simple case would be if theta are the parameters of a multivariate normal distribution. So suppose D has a set continuous variables and they have a normal distribution. So theta is then the mean and covariance matrix of that normal distribution. And that's what you're interested in. and phi are parameters that control the mechanisms, because you don't know why values are missing or not. So the probability that a value is missing or observed could depend on unknown parameters. So that's the phi thing here. But the question does highlight the fact that the interest here, and this is generally the interest in the statistics literature, is in making inference about parameters, not about predicting missing values. Now, you can use the model to predict non-sampled values of D. So certainly you can use statistics for predictive distribution, but predicting the missing values is not really the focus here. The focus is on estimating parameters. So there are conditions for partially missing at random that are discussed in that paper. Okay, so from this full modeling perspective, standard maximum, if you have a likelihood, then you can do the usual sorts of things that we do with likelihood functions. So we can maximize it, get maximum likelihood estimates, maximize with respect to the parameters. And then we can get standard errors, and classical standard errors will be based on some kind of an information matrix, Fisher information matrix, or something like that, or an approximation. So the bootstrap, for example, would be one way of getting it. Could be thought of as an approximation to the information matrix standard errors. Well, in principle, at least. In practice, it might be more complicated. The likelihood could be a complicated function, will tend to be more complicated with missing values. And there might be problems with identifying parameters, particularly if you use the full likelihood, as I'll discuss a bit in a minute. But the point is, you don't have to have a rectangular data set. So you can basically generate a likelihood function and then do what we do with likelihood functions. This approach became more useful, I think, with improved computational power and also computational tools. In particular, there's a factored likelihood for monotone patterns that I'll mention briefly in one slide. The EM algorithm and extensions of EM, notably the ECM, or expectation conditional maximization algorithm, I think is an important one. But then there are a bunch of others. You just add a letter to the thing and write a paper. Mainly in the earlier days for models that assume missing at random, so they ignore the missingness mechanism. Don't try and model the M. This factored likelihood idea is one of my favorite papers, was in JASA in 1957, a long time ago, by T.W. Anderson. Basically said that if you have a joint distribution where you have missing values on Y2, Y1 is fully observed, then instead of modeling the joint distribution of Y1 and Y2, model the marginal of Y1 and the conditional of Y2 given Y1. If you factor, and then for certain models, the likelihood then factors into two pieces that can be estimated using complete data methods. And then you can transform back to the joint distribution of Y1 and Y2 to get the maximum likelihood estimates for those parameters. Clever idea, a simple idea. He didn't bother to go beyond the bivariate case, but it's clear that that can be generalized to more than two variables, and each Y1 and Y2 can be sets of variables. They don't have to be single variables. EM, a lot of you probably know the EM algorithm. So it's iterative, choose a starting value. There's an expectation step, which is not the expectation. The trick in some ways is not calculating the expected values of Y0, the expected filling in, imputing the missing data. It's calculating the expected value of this Q function, which is the expected complete data log likelihood, conditional on current estimates, theta t of the parameters. So there's a Q function, then the M step is simply maximizes that Q function rather than maximizing the full data log likelihood, which you don't have. In many cases, the M step is sort of like maximum likelihood for complete data, which is makes this a very convenient algorithm. Just briefly, good things about EM is that it's often quite easy to program, less easy now that we're looking at very more complicated models, I think, but certainly in those days. The output has a kind of an interpretation. The E step is kind of like imputation, at least for some models. It avoids inverting and computing and inverting an information matrix, so that Newton-Raphson or scoring algorithms will require information matrix, and that's inverting that could be a problem if you have a lot of parameters. Has very stable convergence, and the likelihood increases at each iteration for a very wide range of models. Bad things about EM, it's slow convergence, particularly if you have a lot of missing data. The speed of convergence depends on how much missing data you have. And so convergence can be actually quite hard to establish. Maybe you stop after 10,000 iterations, but 100,000 iterations, it's changed a bit. And then you don't get standard errors out of this algorithm, which is a problem if you're a statistician. By the way, people often compare methods, and they talk about one of the methods I'm going to compare is EM. From my perspective, EM is not a statistical method. EM is an algorithm. So EM is a statistical algorithm for implementing maximum likelihood for a particular model. So the method is maximum likelihood, it's not EM. And not only is it maximum likelihood, it's maximum likelihood for a specific model, because there obviously are lots and lots of versions of this depending on what model you're using. The properties of ML in a particular setting depend on whether you have a good model or not. So the important thing is what's the model, not the fact that you're using EM. I'm not saying that algorithms aren't important. You know, clearly in these days with very large data and everything, the statistical aspect, the computational aspects of this are important. I'm not trying to minimize that. I'm just saying from a statistical point of view, EM is not the method. So I said that we became more Bayesian. So in my view, a lot of you are still stuck in the maximum likelihood world. I dare to say. To my mind, ML is marvelous, but Bayes is better. So why? Maximum likelihood is basically a large sample properties, has good large sample properties. In small samples, though, Bayes is better in my view. And the posterior distribution provides estimates for uncertainty that don't assume that you have large samples. T corrections for normal models, for example. And Bayes is now computationally feasible using these Markov chain Monte Carlo methods like such as data augmentation, a form of the Gibbs sampler, which is analogous to the ECM algorithm for maximum likelihood. When I'm getting people to do Bayes, often I'll tell them to write an ECM algorithm first, and then I'll convert the ECM algorithm into Bayes as the next step. Essentially because ECM is easier to get right because you can monitor whether the likelihood is increasing. So the idea is basically to replace the E step and the conditional CAST stands for conditional maximization here. So the E step's replaced by a draws of the missing values from their predictor distribution. And the CM, instead of maximizing in the CM step, you're taking a draw from the complete data posterior distribution. But essentially, the algorithms are very analogous, but the Gibbs algorithm gives you a full posterior distribution, not just the estimates. Multiple draws then yield a simulation approximation of the posterior distribution. So related to Gibbs, the Bayes is that the draws in that analogous step to the E step in data augmentation can be used to create multiply imputed data sets. So you take these draws of the missing values, and then you create a set of filled in data sets with different draws of the missing values, say m greater than 1. And then you can use simple multiple imputation combining rules to yield valid inferences, provided you have a well-specified model. So this propagates the imputation uncertainty by doing draws, and averaging the estimates over the multiple imputation data sets avoids the efficiency loss from imputing draws. One of the nice things about multiple imputation is that it's valid if provided you have the right model, even if the predictive power of the models is weak, even if what's missing here you can't predict very well. It doesn't matter, since the uncertainty in those predictions is reflected in the inference from a statistical point of view. Multiple imputation can also be used for missing not at random models where you have one modeling the mechanism, in particular for a sensitivity analysis, which I'll say a little bit about later. So these are the multiple imputation combining rules, at least at a basic form. There are some refinements of this basic approach, but I'm skipping them here. So here I'm interested in a parameter, theta, the parameter of interest. You fill in the data as draws from predictive distribution. Theta hat D is then the estimate of theta from the D data set, where there are capital D data sets. Then the multiple imputation estimate is just averaging over the theta hat D over the set of data sets. And then the estimate of the variance has a within and a between component. The within component, W bar D, is just the average of the within imputation variances from the data set, which are complete data variances. And then the between is the variability of the estimates across the data sets. It's just the between imputation variance. And it's this BD, the red part here, that allows for the uncertainty in the imputation. Because if you just imputed and just use the complete data estimate of the variance, you'd be overestimating the variance. You'd be underestimating the variance because there's missing information. This is just an example from a paper way back in a clinical trial setting. So it doesn't matter what the context is, but it was actually an early treatment for Alzheimer's disease. And we did fit some models, and this was something called a continuing dose model. And you'll see that there's a treatment difference. There are 10 estimates of the treatment differences from 10 multiply imputed data sets. And the multiple imputation estimate is just the average of those 10 estimates. And then you can calculate confidence intervals and p-values using these combining rules. And you'll notice that the p-value, for example, for the overall 0.0039 is higher than any of the individual p-values. That's because the individual p-values for each multiple imputed data set is underestimating the uncertainty, or the confidence interval is too narrow for each of those individual data sets, but the overall multiple imputation combining rule gives you a wider interval that reflects the imputation uncertainty. And software now that does all the calculations for you. So the interesting feature, perhaps from a machine learning perspective for some of you, about multiple imputation, that it imputes draws from predictive distribution, doesn't impute best estimates. So imputing means I could impute the best estimate, which would be averaging the draws, and the limit as you average the number of draws, you get a mean, a simulation estimate of the mean, the predicted mean. So imputing means is like averaging draws. Why don't we do that? Well, it's okay if you're interested in linear statistics like means, but for nonlinear statistics, that leads to bias. And as an example, if you were to do this with a covariance matrix, the covariance matrix would then be a biased estimate of the covariance matrix because the variances would be underestimated. And the covariances will be wrong too. So if you did anything based on the covariance matrix, then it's potentially biased. On the other hand, if you impute draws, then the average is, under multiple imputation, you impute draws, which doesn't distort the joint distribution of the variables. but then average the estimates from the completed data sets. And the clever part of multiple imputation is that that works very generally for any estimate, whether it's linear or nonlinear, provided we have a reasonable prediction model. So you have to have a good prediction model, but you have to have that in either case. Really. So imputing a draw from a predictive distribution is clearly inefficient, but multiple imputation corrects for that deficiency by averaging over the data sets. So by averaging later, you correct for the inefficiency. And in fact, multiple imputation is asymptotically, as the number of draws becomes large, as efficient, fully efficient, like maximum likelihood. Sorry, that wasn't meant to be, that should have been there at the beginning. So this is just averaging the estimates from the D data sets. And multiple imputation is popular in statistics because there's a ton of software now for doing it, and this was probably should be updated with some more recent software. But it's just to say that there's a lot of software that allows you to do multiple imputation in SAS and Stata and favorite R programs and all kinds of things to do it. So what about the model? Well, you could assume a multivariate normal model for continuous variables and do that, but then you'd be rather dependent on the normality assumption, which is a pretty strong assumption. This approach, sometimes called sequential regression or chained equation approach, is a nice way of creating multiple imputations because it's really very flexible. So I have a set of variables that have missing values, y1 up to yp. I have some variables that are fully observed, which I'm calling here u. Then the idea of chained equation is that you have a sequence of conditional distributions, y1 and yj given everything else. So y1 given u and y2 up to yp minus 1. y2 given u, y1, y3 up to yp. Yp up to given u and y1 up to yp minus 1. So you essentially have a set of conditional distributions, and then you then have a model, separate models for each of these conditional distributions, and then impute draws based on those models. So essentially you're taking a joint distribution here and looking at it into a sequence of conditional distributions. It looks a little bit, for those of you who know the Gibbs sampler, that's kind of what the Gibbs sampler does, and this is actually pretty analogous to the Gibbs sampler. The nice thing about this approach is that the individual regression models for filling in each of the y's here are very flexible. So you can have different types of, you can have a normal model for a continuous variable, a binomial model, a logistic model for a categorical binary variable. You can a Poisson model for a count variable. You can have mixed continuous categorical type variables. You can have ordinal variables as well. So you can tailor the model for each y according to the type of variables. You can also put restrictions, bounds on the restrictions and bounds on the on these regressions. So it's really a kind of a sequence of regressions. It's not very for certain types of models. This is the same as being Bayes. But these models don't necessarily mesh into a coherent joint distribution. So this method is theoretically a little bit questionable. But in practice, if you model this reasonably carefully, this method works pretty well, and it's much more flexible than assuming a joint distribution to do this sequentially like this. So then, final sort of key idea. Missing not at random models. So modeling jointly, I'm afraid I've gone from R to M here. I apologize, I do that a lot. So M is the missingness indicator here, while the response indicator. So you have a joint distribution for Y and M or Y and R, and then you try and do a likelihood based on that joint model. And that allows you to deal with missing not at random models. However, it's a hard problem since missing at random can't be contradicted by the data. information to fit missing not at random models is very limited sometimes. So a lot of these models are not identified without making additional assumptions. And inferences are highly dependent on assumptions, particularly about the missingness mechanism. There are a variety of classes of missing not at random models, in particular selection models, factor into y and m given y. Pattern mixture models factor as y given m times the marginal of m. But whichever way you do it, results tend to be sensitive to misspecification. The last chapter of Little and Rubin has a more systematic way of approaching missing not at random. So if you're interested in that, you might look at that last chapter. In particular, we talk about ways of dealing with missing not at random. One is to place restrictions on the distribution of y and or m to identify the model. A famous example in economics is the Heckman model for selectivity bias, which is a particular case of a missing not at random model. You could do Bayes and put a prior distribution on the relevant parameters. Rubin actually did that way back in 1977 in a JASA paper. There are lots of other variants of that. Or you can do a sensitivity analysis to assess the impact of deviations from missing at random. And unless you can really justify A, I kind of like the sensitivity analysis approach better than others. But chapter 15 covers this in some detail. So just as a simple example of missing not at random method, here's a relatively simple way of fitting a missing not at random model using an existing software. So I talked about this chained equation, the sequential regression approach, where you model each variable condition on all the others. So if there's a lot of software for doing that. A simple way of fitting a missing not at random model is to take this software, but then add offsets to the multiple imputation. So you just add something that is supposed to reflect the deviation from missing at random. I'm not going to go into any details here, but this is a way of doing it for a general pattern that's very simple. Actually, doesn't require much. All it requires is this chained equation stuff, which is a lot of software for. I did an application of this with an Italian statistician, Caterina Giusti, for a survey with income non-response. This was a rotating panel survey, which is a complicated survey where people who were getting each questions varied across time. The rotation of who gets the survey is plausibly missing completely at random. But income non-response is often thought to be missing not at random. People who respond to income often have systematically higher or perhaps lower even incomes. So we did this offset business to do a sensitivity analysis for deviations from missing at random in this paper. So if you're interested, then you can look at the details. So I have a little bit of time left. So the last 10 minutes or so, I'm going to talk a little bit about machine learning approaches, which I know much less, I have to confess. You know, I'm not terribly good at reading the literature, so I apologize if I haven't read your paper. But I like this. I give this course on seminal papers in statistics, and the last one I cover, it's a sort of history course, is this paper by Leo Breiman, which a lot of you probably heard of, called the Two Cultures paper, which sort of contrasts the sort of stuff that I'm talking about, the statistical modeling, with the more perhaps the machine learning type culture. So you have the setting here was you had a Y, which and then you have a set of predictors. So let's suppose Y has some missing values, and so there's some relationship between Y and X1 to XP. So there's this sort of parametric tradition. So you fit some kind of regression model relating Y to the X's with a function F. a linear model, logistic model, Cox models for survival data, so on. And then focus on learning about F and theta and create confidence credibility intervals, and then do some diagnostics to check that it's not a crazy model. And then there's algorithmic methods that where you don't actually have a specific form for F, you just have an algorithm. So you have like a tree algorithm or mixtures of trees, neural nets, and so on. The focus is on predicting Y, and prediction accuracy often is by cross-validation. And Bryman in his paper talks about two competing principles, if you like, the Occam's razor, which is kind of favors perhaps the parametric modeling thing. Simpler is better. There's a conflict between accuracy and simplicity. Trees are interpretable but not necessarily good as predictors. Random forests are superior predictors, but not very easy to interpret. And then he argues, he's kind of a little bit in the machine learning camp, even though he's a statistician, but if many different Fs have similar accuracy, why assume that one particular F is right? And averaging over many plausible models often tends to lead to better predictions. There seems to be some empirical evidence for that. So in the context of missing data, you could have parametric modeling, which is what I've been talking about mainly. Although, I mean, the chained equation stuff is not fully, it's not, in a sense, it's not a model for the joint distribution, but it's still parametric modeling in spirit, I would say. And then algorithmic methods, actually the early algorithmic method in statistics was this CBS, was the hot deck, which I have a review paper on. But then we could do predictions on the missing values using, for example, trees and forests or neural nets, things like that, or extensions of those methods. So this is where I want to make a point about assumptions. So if you write a full probability model, which is sort of what I've been talking about here, the assumptions underlying that model are explicit in how you're formulating that model. There's this other tradition in the statistics, there's estimating equations, generalized estimating equations, or there are sort of algorithmic approaches, the hot deck being an early algorithmic approach, but then trees and things being also algorithmic, where there don't seem to be any assumptions lying around in those methods. And there's a tendency to think that because Bayes or likelihood methods have this full probability model, then somehow it's making more assumptions than these other methods because the assumptions are being explicitly laid out. But it doesn't necessarily mean that these methods really are making stronger assumptions. All methods lead to some kind of a statistical procedure, a point or an interval estimate. The question is how those procedures work under varied data sets. Whether you explicitly state the model or whether it's implicit doesn't matter. The question is how well does it work with real data sets. Brahma Mukherjee, who's my chair, I can put this thing up. Since I use this in a keynote, we actually did a skit as part of the talk with Brahma was der ex machina. She was this machine learner. But so she gave me the models on the right, on the left, but the trees are on the other machine learning things. So it's clear the models are better. Sorry, not very politically correct. I apologize. So from my perspective, all methods make assumptions, and one of the I like full probability modeling because it makes the assumptions underlying a method explicit and therefore capable of being criticized. Whereas if you show me an algorithm, it's not necessarily clear to me what the real assumptions are. So that I see as an advantage of full probability modeling. Also, rather than making sharp distinctions, I tend to view these clamps as more as different styles of statistical modeling with strengths and weaknesses depending on the setting. And I like Bayes as an overall overarching inference paradigm. And I know a lot of machine learning would agree with that they have a Bayesian view as well. My philosophy is sort of calibrated Bayes, and but I'm not going to go into that here. So we seek models that have good frequentist properties, but then apply Bayesian methods. What about model complexity? For interpretation, simpler is better. Complexity should increase with sample size, so we can certainly try to have more complicated models as the sample size gets larger. Complex tends to win if we're trying to squeeze the last ounce of predictive power, and interpretation is secondary. Complex is not necessarily assumption-free. That's my personal view. And since we talk a little bit about trees, I just want to put in a word. One of the earliest examples of trees was a guy at the Institute of Social Research at Michigan, Go Blue, called Jim Morgan. He was an economist or social scientist who wrote about applying tree methods to income data in 1963, a little while ago. And they had this method called automatic interaction detection, which was essentially a tree thing. And the nice thing about trees is it allows for interactions pretty easily. Although statisticians complained about it a bit, so I'm going to skip over in the interest of time. Okay, so what about trees? Trees are models from my point of view, and they have strengths and weaknesses. The strength is that it allows for interactions. There's no reason why you can't include interactions in a linear model, in a standard model, but there's certainly trees are more interaction focused. But you need everything to be categorical, and creating categorical variables from continuous variables loses information. Often relationships are smooth, and categorizing things loses the smoothness. And it may be more reasonable to give main effects and lower order interactions higher priority than high order effects in a regression model. And lower order effects are also easier to interpret. So, I mean, it's not like, I think, as I said, Bayesian, the additive tree, regression trees I like a lot. So it's not that I'm against trees, it's just I think they're all models essentially. And I'm going to skip over this in the interest of time. But the usual way of predicting missing values in the machine learning methods does make an assumption about the missingness mechanism. That's not the same as missing at random, but it's arguably no better, and perhaps arguably not as good, because it could be less efficient. I'm going to skip over this in the interest of time, but I actually have a paper on this coming out in Statistical Sinica, short paper. I'm going to skip over this just to. So mixing trees, as in forests, seems to work well for prediction. But if you're mixing things, I like Bayes. So you have a set of models, then use Bayes to mix the models. Then the models that don't have as good a fit tend to be down-weighted. So a structured prior distribution gives priority to more interpretable models and models that fit the data better. Finally, I'll stop. Be clear about goals. So one of the striking differences between the statistics literature and the machine learning literature is that, as you've seen from my talk, in statistics, we're clearly interested in model parameters. We could use it to predict other future values of variables. There is a predictive part to statistical modeling, but even that predictive part involves estimating parameters. So in the statistical approach, we have assessment criteria. What's the mean squared error of the estimate? Well, what's the width and confidence coverage of a confidence interval? And I like to ask, is it really missing data? So what would you do? What was the theta you're interested in? What would you do if you didn't have any missing data? Sometimes if you ask that question, missing data goes away because it's not really missing data. Now, imputation of missing values happens in some of these algorithms, but the point of imputation is not to get the best prediction of the missing value. It's to access the information in the incomplete cases. So you're trying to include the information that's observed in an incomplete data set, case. You're not trying to get the best prediction of the missing value. On the other hand, in a lot of machine learning stuff I've seen, the focus is very much on predicting the missing values. The assessment criteria, for example, might be the root mean squared error of the prediction of the missing value, or the coverage of the width of the prediction interval for that missing value. These are different approaches, so it's important to be clear about what your objective is if you didn't have missing data. And in particular, imputing draws, which is what I've been talking about in multiple imputation, is clearly the wrong thing to do if you're trying to get the best estimate of the missing value. If you're trying to get the best estimate of the missing value, you want to impute a mean, if it's mean squared error, or median if it's some other criterion. On the other hand, if you're trying to do inference about parameters, then imputing the mean, which is the best thing from the point of view of prediction, is bad for estimating the parameters because it distorts the distribution. So which you're interested in really matters. And I have a slide that talks about, since I haven't really talked so much about my work, just some things that I've been doing, which you can look at if you're interested. I'm not going to go into it here. Finally, what's the future? Well, I think there's going to be more developments of complex, flexible models to weaken parametric assumptions, algorithms from a computer science point of view that can handle these very large data sets. But particularly, I would favor the Bayesian approach. And hopefully, since this is not always the case with machine learning, some emphasis on capturing statistical uncertainty in estimates, since this is a big part of statistics, and I think it can be neglected if you spend all the time worrying about getting the best estimate. So that concludes my talk. I have a set of references which you can look at your leisure. We'll make these slides available, but thank you very much for listening, and thanks again to the organizers for allowing me to talk.
Great, thank you, Rod. Thank you very much. I put a message in the chat if there are any final questions, but I'll just start. We'll just go a few minutes over for a couple of questions. I was wondering, so I've heard about multiple imputation a few times. I don't know a lot about it, but when I hear people describe the method, they say that you do this imputation of the data, and then they mostly talk about like the following steps, what you do with multiple data sets, how you combine them. But it seems to me the imputation step is like the step where all the assumptions are and all the modeling is. Am I correct? And are the statistical softwares that are out there really like flexible in general and giving people lots of options in how to do the model imputation, or do they make a lot of assumptions?
Yes, so that thank you very much. You're quite right. It's where those imputations, the quality of the inference at the end depends on how good the imputations are, and that the quality of the imputation depends on how good that predictive distribution really is. And so that is the critical feature. And early on, people would do multiple imputation based on relatively strong models, like a multivariate normal model that assumes all the regressions are additive and linear. This chained equation method I mentioned, Raghu, our colleague in Michigan, has a program, IVEware, that does this, and there's also various other programs, is much more flexible. So taking this chained equation approach, you have a lot of increasingly more options for that predictive distribution, including things like BART, for example, which I quite like. So I think the trend is to have a lot of options for doing it, but all of these options make some kind of assumption, particularly the missing at random assumption or something like it is implicit in any time you're trying to use the observed data to fill in the missing values. you're really making something like a missing at random assumption. It's not quite the same in the machine learning algorithm, in the tree algorithms, but there's a similar kind of assumption there.
Okay, thank you. Looks like there aren't any other final questions. Oh, here I have a question from Anru Zhang, who's one of the speakers later in the week. He asked, in your opinion, what are the most important problems in missing data and statistics and machine learning right now?
Well, I'm certainly not going to talk about machine learning since it's not my area. In statistics, you know, there's what you do for missing not at random is clearly a big issue, and there's a feature of that that question that's kind of intractable. You know, essentially, you can't contradict missing at random based on the observed data. So but then there are a lot of alternatives to missing at random that you can implement by making assumptions. And I mean, one of the so I've just the missing at random setting. I have this paper in Clinical Trials, which is doing a sensitivity analysis. That's kind of the way I tend to think about these problems. Then there's robust modeling. So from my modeling perspective, there's making more flexible models. Like I have a method called penalized spline of propensity, which uses the propensity to be missing and models that non-parametrically. So there's sort of more non-parametric types of models, and then there's more flexible models. So that's certainly one that would be my own interest. And then the other thing is, from a computation side, that if you have vast data sets, then can you use complicated iterative algorithms to data sets that have millions of observations? I mean, even with the increases in computation, that's not totally a trivial thing to do. So, I mean, I think in terms of genetics applications, in genetics, people use imputation, but they still don't tend to use multiple imputation, essentially because, I think, probably because of the computational challenge of doing this multiply.
Great. There was one more question. I'm going to pass the hosting off to Boaz so that I can go and open a poster session, but I'll just tell you the question and you can finish. Is multiple imputation a Bayesian or a frequentist approach?
Yeah. So the etiology, the multiple imputation combining rule that I mentioned is based on Bayesian ideas. But to my mind, Bayesian methods are also frequentist methods, in the sense that any Bayesian posterior distribution, you can talk about what the frequentist properties of that inference are. So if you had repeated sampling, what would be how often would the posterior distribution, the 95% credibility interval, for example, how often would that credibility interval cover the true parameter in repeated sampling? So although the etiology of multiple imputation is Bayesian, anything like this has frequentist properties, and the calibrated Bayes idea is to try and use models that give you good frequentist properties. So you're trying to get the best of both worlds. You're trying to use the formality of Bayes, because that's, to my mind, that's the right way of doing statistics. But then you choose models in a way that give you posterior intervals that have good confidence coverage, for example. So they have both a Bayesian etiology, but they have good frequentist properties. That's the goal. I'm not saying it's easy, but it does lead you in certain directions, I think, when you're doing modeling. And it's a little bit similar to objective Bayes, I guess. But so in general, I'm more the calibrated Bayes thing. I think is closer to what we call objective Bayes than subjective Bayes. Although there are some situations where you don't have identified parameters where you sort of have to be subjective.
right. There were a few other questions, but actually we have now 3 parallel poster sessions that start now, and so I think we'll wrap up this session. Thank you, Rod, for a very interesting overview.